Devashri. So my job over the next few minutes and the next few slides will be to explain the model that we have been using and how we have incorporated it in the India case. So it starts from a very fundamental standard compartmental epidemiological model called the SIR model, where the basic idea is that you have a population of say n people and you divide them into states or compartments according to what situation they are in terms of the infection. So if they are not infected yet, but they can possibly be infected in future, we call them susceptible. If they're infected now and can be spreading the infection, we call them infected. And if they have either recovered or have died, we call it removed. So we are not distinguishing between recovered and death here, but that is also possible in some variations of the model. And the utility of structuring it this way is that you can model transmission using the observed count data for the infected and the removed. The real challenge is that you never really can observe the exact true numbers and therefore the true proportions of these things in the population of your interest, because for several reasons, including different kind of testing selections and test imperfections and others, you cannot perfectly have your infected cases all traced, and similarly for the recoveries and deaths. So how do we go about that challenge, and how do we still use this SIR kind of structure to address for the fact that we are not observing everything that's happening in the population? The idea that we used is an existing previous model that was formulated and also implemented as an R package by the Song Lab in our department, which is called an extended SIR or ESIR model, a structure of which you see here. The basic idea simply is that you break up your observed and true latent proportions into two layers. So the bottom layer you see there, the red triangles that you can see with the marking latent SIR model, is the actual latent true proportions of the SI and R compartments denoted by the thetas. So that's the part you cannot observe, but that's the part on which the true SIR model is actually running, like a Markov process, in the sense that the numbers that you see today are conditional on whatever numbers were there yesterday, so on the past observation time. Conditional on that, you have a top layer that you can see denoted by the Ys, which are basically indicating the number of observed or the proportion of observed infections and removals. So YTI, for example, would be the proportion of observed infection with respect to the population size that you have observed at time t. So based on this structure, we are now going to put some mathematical formulations on this to get a solution of this system in a Bayesian way. So we start with the very basic SIR model that is on there on the latent proportions. So that is described by this system of differential equations that you can see here. Intuitively, what it says is that the decrement from the susceptible compartment and the transmission from that to the infected compartment happens proportionately with the number of interactions between the susceptible and the infected people. So that is represented by the term theta ts, theta ti, and the beta is basically like a transmission parameter, which is basically a proportionality constant there. That is then in turn added to the infected compartment. And from the infected compartment, the removal, which is either recovery or death, happened as a total rate of gamma, which is again proportional to how large the compartment is, which is represented by theta ti. Now, the idea is that this is the model where the SIR happens at the latent state. Conditional on these proportions, you put a model on the top layer, which is the observed layer of infections and removals that are represented in the next two equations. So as you can see, we put a beta distribution on there, and the lambdas I will be talking about a little bit later, which basically in some way handle the scaling there. So that is the top layer. In the bottom layer, you now need to introduce some sort of Markov kind of dependence. So introduced by this equation, where basically say that conditional on your previous time points proportions, your current time points proportions follow a Dirichlet which has that kind of a form, where f is basically an abstract arbitrary kind of function. So, and also kappa is basically a scaling factor. So that, because you have structured it that way in the latent system, that introduces marginally a correlation in the observed system of y as well. So because we do not know what f is, we need to estimate for that, and that can be solved in a discrete differential equation kind of approach, which we have not described here. So basically, the model, to sum it up, has two layers. One is the compartmental specification conditional on the latent proportions for the observed proportions, which is the top set of equations, and the bottom set of equation on the latent proportions is what defines the autocorrelation in the entire system. From here, you can extract one more parameter of interest, which is the ratio of the transmission from susceptible to infected and from infected to removed. So basically beta by gamma. So if you go one step further, you will get something called the R, or the reproduction number, which is represented by beta by gamma. And that can be an effective or a time varying thing, or you could also look at that at the beginning of the pandemic. In that case, you would call it a basic reproduction number. So next slide, please. Next slide. Yeah. Okay. Now it changed. So the latent proportions, which are basically the thetas at the 0th time point, you put a prior for them in this way that you basically construct a Dirichlet structure with the observed proportions at the first time point. And also similarly, after you have put that structure for the third compartment, you basically define it in a way so that the three compartments add up to 1. Now comes the important part, where for a Bayesian formulation, we need to put priors on the parameters. So we first think about putting the prior on the R parameter, which is basically the reproduction number, or R naught, which is basically the basic reproduction number. So we put a log normal distribution, and you can see some fractional numbers there. But what that means is that the prior mean of R naught will thus be set at 2. And that is really specific to the region of interest that you were looking at, because we were looking at India, and because all the initial studies, including our ones, were indicating that that's possibly a sensible value to use for there. We used a value of 2. So depending on where you were applying this method, you would be adapting that to a different value. Similarly, for the removal rate from from I to R, which is represented by gamma, you do a similar log normal distribution, which will set the prior mean at 0.082. What that means is that because these transitions in the SIR setting are happening like an exponential process, so you can invert that to get the average infectious period. So average period of time a person stays in the I compartment. Inverting that, you will get that number to be around 12 days, which again also fits in the group of SARS type virus based on whatever previous studies have been constructed. So again, depending on what kind of a pandemic you are looking at, you can reconstruct and adapt those numbers. The thing is that because R is defined as a ratio of beta and gamma, once you put these two priors, you do not need to specify prior and beta separately. So we more or less have the formulations, except for one additional thing, which will be described in the next slide, which is that I mentioned a few scale parameters like kappa and the lambdas. The idea there is that you put a prior which has large variance and less precision, so that you can tune that with more data coming in. So once you do that, now you basically have a sequence of data that you have observed, and then you have to extend, you want to extend your predictions up to the day. So for example, if you had 10 days of data and you wanted to extend your prediction to 5 more days, your T naught here would have been 10 and your capital T would have been 15. So if you have that kind of a setting, based on whatever observation you have already got in terms of the Y's, what you do is you take M independent draws from the posterior for the thetas during the observed time period. And for each of those independent solution paths, you'll be iterating between the two steps that you see below via MCMC. So it'll be at one step, you'll be updating from time point T minus 1 to time point T in terms of the thetas. And once you have done that part, which is the latent one, you would go to the observed one, which are the Y's. So once you've done that, you basically have M independent solution path throughout the whole time when you want to predict this whole thing. Now, what is the utility of that? The utility really is that because of that, first of all, you get a full posterior sample for all your parameters and also all your proportions that you are interested in. And because you get a posterior sample, the nice thing about that is just by looking at that posterior sample and by computing, say, the quantiles of that, you can actually get an idea about the uncertainty. For example, if you had to compute, besides estimates, a 95% confidence interval for any of these parameters, all you need to do is that looking at that set of posterior samples that you have and compute the 2.5 and the 97.5 quantiles, for example. So you can use those percentiles and all to get an idea of the uncertainty. This is how the typical posterior distributions of the Y and theta proportions look like. So the first plot you see on the left is looking at compartment I, and the second plot you see in the middle is looking at the compartment R. So those are basically corresponding to the infected and the removals. And because you get both Y and theta, you get an idea about both the reported observed and also the unreported cases, which is represented by Y combined with all the unreported cases of the total in terms of theta. Also, you can look at other things. For example, Y and theta both are formulated in a cumulative manner, but you could go to, say, for example, the daily increase or the active number of cases. For example, if you wanted to look at the daily prevalence in a mathematical continuous time form, it's basically a differential with respect to time of the compartment that you are looking at. When you look at some output like this, you could just discretize that and look at your time steps and compute it from there as a difference. So that up to whatever you see now is our model. Without telling the model, whatever implementation of any sort of intervention has happened throughout this time. So how do we bring in interventions like lockdown or other kind of non-medical interventions? The way we do it is that we say that what does an intervention really do? The intuition is that it really decreases the interaction between the susceptible and infected compartments, and therefore the transmission from susceptible to the infected compartment happens in a less proportion. So for that, we bring in a parameter called pi, which is a time varying parameter denoted by the t there, which is basically between 0 to 1, and which brings down the beta parameter of transmission between those susceptible and infected compartments. So now our updated set of differential equations, instead of beta, will have beta pi t. Therefore, our effective R will be now, instead of beta by gamma, it will become beta pi by gamma. So basically, it will be pi proportion of whatever the R was before. And we use some really specific schemes according to the governmental interventions in India, and Max will be explaining those things next.